guess. Yes. So now we have Anubis Networks guys, Pedro and Joao, and they prepared their work with Ludwig Krippal, and you have the floor now.
Thank you. So we are here to present our work on how to detect botnets, and we do this. This was a joint work, mostly Pedro's work, and a joint work with the university, with the new University of Lisbon, where I work, and also Ludwig Krippal. So. I'll just do the introduction. I'll introduce myself and Pedro, and then I'll give him the floor so that he can explain what he did mostly. So Pedro just finished his masters in engineering at. So actually, it wasn't last week, as it's written there. It was 2 weeks ago. But okay, so this is mostly the outcome of his master thesis. So he's a computer security enthusiast, and now he's working for the R&D team for at Anubis Networks. So I'm almost finishing my PhD in artificial intelligence. So it's an unrelated field, but hopefully it's useful in computer security. I also work for the R&D team from Anubis Networks, and his professor, so his coordinator, was Ludwig Krippal, and he's from another unrelated field. So he's originally from biochemistry. And he has a master's in applied artificial intelligence, which goes to show that this cross-pollination can really be interesting. So we can use different skill sets from different areas, and when we apply these skill sets to computer security, in this case, we get nice results. So I'll give the floor back to Pedro.
Thank you, Joao.
Yeah.
So I will briefly talk about botnets. You already know how they work and what type of evasions they have. So they are usually composed by one master or more nodes called C2 or CNC from command and control. They have evasion techniques, and they are requested by a black hat client. Very often, black hat groups implement or use an existent botnet that they implemented already, and they use the infected devices from that botnet to execute commands that are ordered by the C2 to fulfill its objective. We will be focusing on that zoomed section in the middle between the C2 and infected devices that may have different types of topologies. I'll talk now about the evasion techniques that some of them I consider to the detection, some others are just not possible by the means I use. So often encrypted communications make it difficult to use payload data, but we can still use metadata like payload size, payload, other meta info from the payload. We watch also fast flux and double fast flux DJs and other means that are just creative and difficult a lot to make an effective detection. So this is a typical fast flux. This is taken from the Wikipedia. You are used to it, so I won't be explaining. But in a small in a small phrase, it's just a lot of records for a small period of time, and this is done through a low TTL value. They have DJs. Some of them are random based, some others are dictionary based. This particular one, it's a dictionary one. It's time sensitive, as you may see in the code. And this one is just a creative one that is implemented or was implemented on Necors that used a legitimate domain to get its CNC IP. So it just alter the bits on the third octet and get CNC IP. So detection methods, the part that matter. We divided this in two main types, passive and active detection. On the passive one, we highlight packet inspection and domain name syntax. We weren't able to use network flows because we just can't have network flows info from the data we have. For the active detection, we use domain name resolutions to detect fast flex behavior. The other two methods are information correlation from other services and the graph-oriented queries. On the packet detection methods, we have this kind of info. We use it to group same pattern traffic, discarding destination, source and destination information. On the first one, on the second one, we use that information. We correlate IP connections by common destinations. On the DGAs, as I told before, we have two types, random and dictionary based. I won't be detailing the attributes that we used here on the classifiers that we'll talk after some slides after. It will be on the paper that will be published on the BotConf website. So we can use that kind of attributes or ratio, consonant ratio, domain name length, and other ones. The dictionary-based ones are a particular case that it's really difficult to have a machine learning approach, at least by the attributes that we used on this work. Domain name resolutions, it's just record the historic information for an IP to see its IPs. In this particular example, we can see a change of the A record in the example.com domain. And the detection methods, the two one that we'll talk now will be about the machine learning approach to the problem. The first one is one where we try to detect random DGAs, domain names. In this case, we can see that some of them were just bad classified. It's an error, and we can't avoid that in machine learning, unfortunately. But it's as you can see, most of them were detected. Unfortunately, fubar.com too. So now the really interesting part. Here I group same pattern traffic where I only see the host information, ATP code, ATP version, method, size, and I also provide the DJ, the result from the classifier, but I don't use it to group the traffic. But here you can see, this is an example, it's fictitious, it's not real, but you can see that we could see this happen. In this example, you can see that the two IPs that connected, that two domains have the same pattern if we don't look to the connection, and they are the same family. They maybe they just don't are the same group or the same campaign, but are the same family. So we used neural networks to do this, more properly self-organizing maps. For the information correlation part, we used information from our sinkholes, IP reputation services, malware analysis, and historic DNS information. I developed a system called DNS crawler that will give some info about domains that were in FastFlux. On the graph-oriented part, we use a time frame, like 6, 12, or 24 hours. We just make a query to discover what domain names appeared on that period of time, and then we correlate with information from the double time of the time window we are looking. If we were looking for 6 hours, we would watch for 12 hours. If we would watch 12 hours, we would be looking to 24 hours, and so on. But the sky is the limit. If you have more information that can be correlated with this kind of information, it will be very useful. And graph-oriented approach, it's shown very fast when compared to other databases available. So here I try to show what kind of clusters we get. In this case, we only look to the IP connections, source and destination, and can't discover same campaign or group clusters. On the second one below, we can find another one that happens to be the same family, but we aren't unable to correlate this or to discover this. So we used the neural network to group all this information together. Here you can see that even not intersecting by connection, we can group same types of malware by pattern. So we find the family cluster. So let's wrap up everything. For the DGA domain classification, we use the support vector machine. For CNC detection, we use DNS information. And so the fast flux and double fast flux. For DGA rotations and last hour alerts, we use the GraphDB queries. We group similar traffic with self-organizing map, more properly a neural network. And if we want to get same botnet traffic, we only correlate information from common destinations. If we want the same botnet family traffic, we correlate IP connections by machine learning clustering process. We also can do direct classification by malware analysis, and IP reputation. It's interesting indicator too. So demo time. So this is an example of the classification process. I must thank Daniel from the DJ archive because it was very valuable. I will use a domain name from CryptoLocker, a domain from today, to do this. Look at this. So it classified 144 types of DGAs. But for example, if I put there botconf.eu, I won't find anything. Or other things like google.com, your company name, Microsoft. What do you want that I put here? Microsoft. Awesome. Actually, it's a push to. Okay, this could happen. These have an error rate. It's not perfect.
But it's Microsoft.
Yes, yes, I noticed. I noticed. But it can happen that I give a valid domain name like I don't know. Let me see. BotConf something.com. Okay. It's not perfect, but it's an interesting indicator. So now this was the classifier part. The other part, the group part, I have here already form cluster where I only grouped things that are in the same cluster, and this was grouped through the neural network algorithm. I grouped the same traffic. I'm not even looking to the source and destination. This is all in the same domain. This is the same domain in the same cluster. Right. And you can see that this is the same thing. You often have some other information or don't have. In this case, you don't have method. But it's here you have HTTP1, the other ones don't. Let me see. Next part. This is an example. Another example. I think this is Mevade. I'm not sure, but this is an alert from our system. There is something going on that domain, and it happens to be on 3 countries. They are all old IPs. We saw them before. So it's probably a rotation. And in this case, yes, it is. We have here other domains that are from the same cluster. And I would like to thank again to Daniel. This was really useful to prove the classification. It's work like this that happens to be really useful to our work as researchers. So let's return. This one, right here. Okay. So I'll conclude. We have a lot of problems. We have distinct topologies, evasion techniques, humongous traffic, bad actor security. We have some solutions. Present versus past, real samples, the InfoSec community. This all, it's useful to correlate relevant information. In the academia, we have machine learning, other fields, and other kinds of work that may be useful for this work. I would like to, the next slide, it's a funny thing that I saw yesterday here. So to whoever did this, thank you. It made me laugh. Thank you.
Time for questions. C'est Pedro qui a le... Enfin, Joao qui a le...
No.
Thank you.
Questions? Come on. So who does automatic classification?
There's some guys here.
Yeah, Peter. Okay. And you have no question? T'as une question, Edouard?
Hi. I also have a machine learning background, so can you please tell us more about the features you use for the SVM or the
Yeah.
kernel you use?
Some of the features are here. Okay, here. For the classifier, we use follows ratio, consonant ratio, domain name, and all the features are based on the string of the domain name. On the other algorithm, neural network, this one, we used other information like the number of the HTTP code, the method, the size, we joined here the domain name classifier features also. We have a total of 81 features for this algorithm, and this one we have total of 11.
And is it a multi-class classifier that gives you the botnet that would use this DGA, or do you have one classifier per botnet, or how do you do that?
We have one classifier by botnet.
Okay. Thank you.
On the paper, there's only one. We joined everything and did one classifier, but now we are using separate.
Okay, thanks.
Another question? Holly? No, it's not Holly.
I'm just curious about your training set. How big is it?
You were talking about the
For instance, for your neural network.
a neural network. We used for training. We are batches of 10K.
Okay, good. Interesting.
One. Oh, over there.
Thanks for this presentation. How did you manage to build your ground truth for the training set? The ground truth for your training set, because in the demo, okay, I want to understand there is some, it's not perfect. Okay, there's some anomalies, but in your opinion, what are the reasons? It's because your ground truth, because of your learning set, or it's because you are missing some features that you need to add?
So the idea is that we can put inside so clustering works like a bag. So you throw stuff inside, you shake the bag, and then the little stones get together, right? So our idea, in order to validate the clusters and to see if they are properly correlated, is to throw in some domains that we know belong to some malware family. So, for instance, if we go to VirusTotal, there's a list of domains associated with some malware family. We take some samples, we throw them inside the bag together with other domains that we know nothing about. We shake the bag and we and we get okay. But it's very difficult to obviously it's very difficult to know if we are making the proper groups. He used some metrics, but they say things that are inherent to the cluster itself. So some indexes, some silhouette index, and some metrics that are not. They are only indicators of the clustering process itself, but they don't say anything about how good the clusters are. Okay.
Last question. Okay, thank you.
Thank you.
Okay, so a few comments before we leave for lunch. So first one, this presentation was a short talk. It was typically exactly what we expected from short talks. He's a young researcher presenting his job, and it's exactly what we wanted to have here. Before there was a presentation from Google. Google is one of the sponsors, of course, but they went through the whole process of with the program committee and everything, so they were selected and not just appointed because they're sponsors. Same goes for David, who's from Trend Micro tomorrow, and they had to give their papers in time and everything. So it's not just because they're nice sponsors. It's because it was an interesting talk to look at. So that's for the program. Last comment, I'd like to see Paul Jung before lunch if possible. And I wish you a good lunch and see you back in 1 hour. Okay?